Greetings, AI students. We're going to pick up where we left off working on this data, this MNIST grayscale 28 by 28 images of fashion. Okay, and we've imported all of those as part of TensorFlow. TF is TensorFlow there. And we've looked at the data and visualized it. And now we're going to build that feed-forward neural network, which you'll remember, okay, looks like this. We're going to have inputs. We're going to have a hidden layer of neurons, each of which has, input from every input is going to go into this neuron and into this neuron, and then we're going to have 10 neurons in the output layer. One is going to light up for each category, and we're going to try and build this network so that at any given time only one output neuron lights up intensely and the others are very dim. So that's where we're going. Okay, this is the model. The model is an object that contains the architecture of your network. All right, this input thing says it's going to be 28 by 28. And you remember the images where each image was a 28 by 28 array. All right. This next thing is kind of weird. It just flattens it. So it'll just take that 28 by 28 and turn it into a single list of 784 numbers. All right, fine. And that turns out to be very useful for feed-forward neural networks and a lot of other purposes too. Our next layer is that hidden layer. Those are the layers in the middle. We have 128 of them here. And the function in the middle is this ReLU function, which you've seen. So positive numbers just flow through, and negative numbers are turned into 0. This is the picture of how those things work. And all those, that 784 inputs coming into one neuron, 784 inputs plus one bias. All right, multiply, add them all up, and then if it's negative, nothing comes, 0 comes out, and if it's positive, the same number goes out. That's ReLU. Okay, so back to here, we have a layer which is called densely connected, means that all the previous guys are connected. Crosswise, all possible connections. 784 inputs times 128 middle ones, densely connected. And then we'll have our output layer where we have 10 neurons, one for each category. Okay, we'll have, where was this one? 10 output neurons, one for each category, like that. And we're going to give it a different output function. It's called softmax. And softmax is kind of what you think. It's going to fix it so that one lights up more than the others, but it's not crisply saying one of them goes all the way to 1 and the others go to 0. It's going to sort of push the higher one higher and the lower ones lower without going all the way to 1 and 0. If we go all the way to 1 and 0, it's probably never going to train correctly because we get a wrong one and we're stuck. But the other thing about softmax, which is interesting, is that all of the output neurons are going to communicate with each other. So if we go back to this picture over here, these output neurons all talk to each other so that in aggregate all their outputs add up to 1. So it's not like each neuron is operating individually. They're coming to an agreement so that they each have their values, and then they will adjust their outputs according to their values and according to their neighbors, so that the lower ones are lower, the higher ones are higher, and together they all add up to 1, all of the output neurons. So that's a very useful, kind of expansion on the idea of what happens in a neuron by, having a layer of neurons which are going to cooperate together. Okay, so that's your last layer over here. Again, it's densely connected, and that's our activation function. It's the softmax. Okay, and then here's a explanation of these guys. And remember again that our outputs are going to light up one LED instead of, okay, like that. So this is ideally what we want to have happen. Okay. So we call that one hot encoding, which you've probably seen from other classes, but if you haven't, that's the idea. One of these outputs is lit up and the others is not. Okay, we'll do a summary here, like we did before. Now instead of two trainable parameters, we have what? Okay, well, the flattened guy is going to be producing a single array of 784, right? This is 128. So we're going to have, for each of these neurons, we have 784 inputs plus one bias. So it's 785 numbers for each of the input neurons there. Okay, so each of these has 785 weights coming in and the one bias, right? Okay, so here we are. That's 100,000 and some trainable parameters right there. Wow. Okay, then we have 10 output ones. Each of them has 128 coming in plus the one bias. So 128 times 10 output neurons, so it's another 1290. So this is the number of weights and biases that are going to be trained in order to make this neural network work. And they give you the summary down here. So I highly recommend that you look at your model summaries to just get a feeling for how that works and what I just explained. Okay. Compiling the model, you remember, is when we tell it what's our error function is going to be, and what our optimizer, our backpropagation for adjusting the weights, for nudging the weights. Now, okay, you did one neuron by hand using a very simple algorithm, all right? We won't go into what ADAM is. It's really common, but it does a kind of what's known as gradient descent. This loss function called sparse categorical cross entropy. So if you remember information theory, if you ever took it, anybody who had my 372 class would know that you could actually do a fair amount of data mining and data compression and all kinds of things using concepts of information entropy. But this is what we frequently use for measuring the error in classification tasks. So think of it as, the correct size of the sets, of the categorizations that it applied to the actual data versus the categorizations that we really wanted. And you can do a kind of entropy calculation to measure how close the sets are to ideal. And so that kind of information theoretic calculation can be used to compute our loss function. We're also going to print out accuracy, just percent correct, all right? We don't need it for training the neural networks, but this entropy number isn't going to make a lot of intuitive sense to us. The percent accuracy tells us in a way which we humans understand, this thing is, 98% correct, like that, okay? So we can get that also in addition to the loss function. But so the loss function is what we use for the error for training and backpropagating and nudging the weights, and the accuracy is what we use for our own trying to understand how well it works. Okay, this is now going to run 10 epochs of, here's the training images, the 60,000 by 28 by 28, Here's the 60,000 categories, one for each 28 by 28 image. We're going to do this for 10 epochs, 10 times through all 60,000. So let's get that started. And you can see epoch 1 there finishing up in just a little bit. We notice that each epoch has 1875. What is that? Well, we're doing the thing with batches. It's putting the data through in batches, as we discussed in class last week. Okay, I didn't waste your time watching this thing do the middle part of its training, but we're just about done with epoch 10 over here. And what have we got? Well, these were the fashion images, which we already know that data just looks worse and harder than the digits. And we got what? We got about 91% accuracy over here. Okay, this is our loss function, and we can see the loss function is going down. It started up here after the first batch. Okay, 1875 times 32 is about 60,000. So the data went through with 1875 batches of 32 each. Where after each batch, it then went and applied that atom accuracy, function to nudge the weights. So it was 1875 batches of 32 was one epoch, one time through the 60,000 data. Okay, and we got up to about 91%. It's it's kind of flattened out here pretty quickly, right? Okay. It's not great, but on the other hand, when you consider that we have 10 categories, just randomly guessing would give us 10% accuracy, right? So we went from monkey score, where you just ask a monkey to pick one, of 10% accuracy up to 90% accuracy. It really has learned basically how to do this task, even though for a lot of purposes 90% accuracy wouldn't be good enough for an industrial application. It's not bad at all. It's actually pretty good machine learning. And it's the sort of thing where if you actually use it industrially, you'd probably have another step where a human was checking each of the outputs or something like that. Okay. Now let's try it on the test images. You'll notice we have 10,000 test images, and we have the 10,000 layout. Now let's give this a whirl. And what do we got? It's 88% instead of 91%. So on the images it hasn't seen yet, it's doing a little bit worse, about 3% worse. Still basically the same, but it's a little bit worse.